Alright, so in this one we're talking about this, if we have a sequence that converges, then the right shift of that sequence also converges. So the statement of the problem goes that if AN converges, right, we're not saying what it's converging to, then the sequence BN, which is essentially sequence AN, but the first term is a 0, right? So we're sticking in a 0 and we're shifting all of the rest of the terms to the right. And our claim is that that also converges. So in the proof, we're going to assume we have some sequence of real numbers that converges, and we're going to prove that this right shift converges by showing that it satisfies the definition of convergence, right? We're going to show there exists a real number a, so we have to construct an a, such that for every epsilon greater than 0, arbitrary epsilon, there exists an n, which we need to construct, so that all of the little n's past it, we have b sub n minus a, and again I've made it explicit, and I'll show you why this works a little later on, is less than epsilon. Since we have a convergent sequence, it has to converge to something, so there exists a real number a1, such that for every epsilon greater than 0, there exists an n, such that for all n greater than 0, we have yada yada yada. Okay? Basically, it satisfies the definition of convergence. Now, we're going to choose such an n1. We haven't proved in class that these are unique, so there could be lots of them. So we got to pick one. So let's pick one. And I'm going to set the a we're going to use in our proof equal to that a1, right? So now we have constructed a. Now we're going to let our epsilon greater than 0 be arbitrary. And what we're going to do is now we're going to construct our capital N, right? Since AN converges to A1, there exists an N1 such that for all the little n's past N1, we have AN minus A1 is equal to this epsilon that we now have as an arbitrary thing. So we're going to pick one of those. If there's one, in this case there's an infinite number, we want to pick one, and I'm going to set n equal to 1 greater than that to take care of the fact that we are shifting our sequence to the right. Now I want to consider n greater than or capital N to be arbitrary, right? So for such an n is greater than n1 plus 1, and n is greater than 1. So this b1 equals 0 is not going to be a term that we're going to be considering. So for this n, b sub n is equal to a sub n minus 1, right? You notice that b1 was 0, but b2 was a1, b3 was a2, right? So bn is the a of 1 less than that, right? But we have constructed n to be greater than n plus 1, so n minus 1 is greater than the n1 that we used in our construction. So if n minus 1 is greater than n1, that means a sub n minus 1 is within epsilon of a1, which is what we constructed to be our a. Thus, for our bn's, bn minus a, well, bn is an minus 1, a is a1, and that, as I just said here, by our construction of a1 and n1 is less than epsilon. Therefore, bn minus a is less than epsilon. And we proved the thing that we wanted to show.